Hello and welcome to our 27th lecture, the integration rules and table. So today we will learn how to solve the integrals and we'll get the table with the common ones that we can use when we're referencing back. So a quick refresh from last time. On this image is the integral notation for the finite integrals. If we didn't have the limits, we would have the indefinite, the one that's written on the top. And if there's no limits, we have to add a plus c after the antiderivative that's marked with a capital F. So I do have to add that when you need to solve integrals, you may not always have the integration sign given. Rather, you will have a function and the differential of the variable you need to integrate, like here. And then if you have to integrate, you write the integral sign and solve it and whatever. But like, you won't always have the integral sign when you have to integrate. Sometimes you'll just turn around the derivative and it will become an integral. We have 4 core rules for solving, basically for simplifying functions, so it's easier to like use the rules or methods on them. So we have rules for addition, subtraction, or presence of constants. However, for stuff like multiplication and division, it gets complicated, so we don't have the rules or formulas, but methods, which are like multiple steps of rules, but yeah, we'll see. Some of which I will explain, some I will just show as they're a bit more complex and would either need their own shorter video or a lot more time. But I do show some videos that other people have made that are very well made. But if you do want to see me make those videos, just using those methods on examples, please tell me in the comments, because I really love feedback and I'm always on to explain more stuff if people need it. So for the 4 rules, the first one is the constant rule. The second one is the power rule. Then we have the sum or difference rules and the constant multiple rule. These rules will be the foundation of today, and everything else will basically build on this. And all these rules and methods I mentioned later are obtained from derivatives like the power rule, that we will just undo it there. So to start with the constant rule, it's when we have an integral of a constant, the result will be that constant multiplied to the variable we're integrating plus c. So the integration constant, so c is the integration constant. Since this is an indefinite integral, this will be always present. However, if we replace this x with any other marking or even a function, in an example where k is 1, the result of integration would be the function itself with the c added. This was kind of not explained last time, but I think I had it in the mini test, and now we see the rule in front of us, which kind of makes sense. And of course, this comes from the power rule of derivatives, where we had something like a derivative of 2x being 2, and in this case the k is 2 and integrating must give us 2x back. So somehow like that, as x is in itself a function, albeit a linear one. So I think this comes in handy later, but this could be x squared, this could be e to the power of x, whatever. But yeah, so an example, like I said, the integral of 2 dx would be 2x plus c. And an integral of dg, where the g is the symbol for the function of sine of 2x, the result would be a sine of 2x plus c, because, well, the function in the differential form, or however it is said in English, is being integrated, so it's just present. You know, that's kind of it about it. Next up is the power rule, about which I hope I don't have to say much, as we mentioned it last time and we know what it is in derivatives. So we just undo that. So we increase the exponent by 1, then divide the result with that new exponent, plus a c at the end of it all. And we have solved an example last time, so I will show you where this rule kind of breaks. I'm sure you have figured it out. It's when you have n equal to -1, or when we integrate 1 over x, as our result would be getting divided by a 0. So that integral, or this integral, will equal to the natural logarithm of absolute value of x plus c. Why the absolute value? Well, think about it. Logarithm stands for the exponent we raise the base to get the number inside the logarithm as the result. So basically this entire thing refers to the exponent, and the x here is the result. So does there exist an exponent to which we would raise the positive constant e to become negative? Well, no, there doesn't, at least for the numbers we have. So we add an absolute value so that we can insert negative x values so as the result of exponentiation, and still get the result. This will be one of the integrals on the table, of course, so do not worry. The third rule is the sum and difference rule, so how we integrate when we have a sum of two functions that can't be added into one. For instance, 2x and 3x can be added into 5x, but x squared and sine of x cannot be added into 1, if that kind of paints the picture. Well, let's think again back to derivatives. We remember if we took a derivative of a sum, it was the same as the sum of derivatives, so same principle applies here, as there is no convoluted formula. So from that we get that the integral of a sum or a difference of two functions or more is equal to the sum or difference of the integrals of individual functions. So let's take an integral of a polynomial 3x squared plus 2 dx. We can integrate each individual part, and following the power rule we get the x cubed plus 2x plus c, because each individual would have a c, but then again at the end is just one constant, so we can just combine them. We will see this in differential equations where we simplify it by introducing a new constant. Here we're not gonna overcomplicate it and just set it as c because, well, it's a result of one integration, won't change much. It's like plus 5 plus 3 equals to plus 8. So we could just set this c as an 8. And for our last rule, it's when we have a constant multiplied to a function, and just like with derivatives, the constant is multiplied to the result like this. So we can carry the constants out and multiply them to the entire integral or its result or whatever, which comes in handy in simplifying integrals when they get a little bit more complex, as we will surely see later. So combine the two of the rules, we would solve an example like this. We have a function of x which is 5 divided by x and dx after it. This means that we can integrate it. So quick note, again, you don't always have to see the integration sign. As long as you have the function with dx multiplied to it, you can integrate. So let's combine the constant multiple rule and the power rule. Carry the 5 in front. The integral of 1 over x dx, to which the result is logarithm of the absolute value of x. So the overall result is the 5 times natural logarithm of absolute value of x. And I hope this was all clear, as these rules stem from the derivatives, which come from limits and so forth and so forth. They aren't really that complicated. You just gotta keep in mind on how to use them correctly. Now that we have the basic rules, I present to you the basic integrals table. So as we can see, top row is the basic power rule, its expansion for the exception of the exponent being -1, and the one where it's just a constant that I changed last second. That's why it looks a bit off. So a constant times the f of x. This is because sometimes you will have some constant and then a differential of the function, so that function will just appear in the result. And the constant will be a 1 for a lot of examples in physics. Then on the left we have the x in the exponent for the first segment, so some other constant and some e. And then the logarithms in the second segment, and on the right we have trigonometric functions in the first segment and inverse trigonometric or arc functions in the second. Well, this will be handy going forth, and let's try to remember it, okay? So, now that we know the basic rules, the table, it's time to learn the tricks. The first trick is linear composition shortcut. So a trick that we can use whenever we have an integral of a function that has a linear function inside of it. So we can't use it if we have some exponent to the x or so. So let's see an example. So we have an integral of sine of 3x plus 2. So we see this comes in when we have a composite function of a linear function inserted. So we will integrate the sine function to get the antiderivative. And following the table, we get minus cosine. So we get the minus cosine and insert the linear function as is shown here. So just as if it was like a normal x. However, for the correction, because it's not just the x, we will divide it with a. So the factor multiplied to x. In our case, this is 3. And after that, we add a plus c at the end, and that will be our result. Why does this work? Well, to be honest, I don't really have the exact idea, but I do know it comes from the chain rule. Oh, no, never mind, I got it. When you differentiate, you multiply with the derivative of each function. So the derivative of the inner function would just be the factor in front of x, because everything else disappears. So multiplying that would cancel the 3. I did check it, and some y only works for linear inserted functions. So sadly, we cannot generalize it for like x squared or whatever. Maybe there's a way, but it's way above my pay grade and it would be much overcomplicated for you. So I'm not gonna bother you with details. This is just one of the rules that makes it easier to solve simple inserts. As we will see later, the inserts can get quite complicated. So let's solve another example like e to the power of 2x. So I set the integral sign, I write out the rule, I color code so it's easier for you to see what's what. So the function is colored in orange and the linear insert is green. And the a, so what's multiplied to x, is a slightly lighter shade of green, because yes, now we use the table. We see that the integral of e to the power of x is e to the power of x plus c. So our antiderivative would be e to the power of some constant, so x in this case. We just copy the entire linear equation, linear function inside it. We add a plus c, and after that we just have to divide with the factor of a, so the one that's multiplied to x, so that's a 2. And once we do that, we get our result of the integration. It's a simple, straightforward rule. You can dig back to where it comes from. Makes it easier to remember, because if we remember the chain rule, it was the derivative of certain function with the g of x insert was like the derivative of x, where technically we had the g of x inserted, and then we multiplied that to the derivative of g of x. So technically this is our g of x derivative, because, well, x disappears, the constant disappears, and this is our antiderivative, so going backwards, because like we're undoing this, so this part is present on the left side, and since this derivative of g is not present technically here, because it's like just the derivative, so technically this is f prime of some g of x. We're missing this to complete the rule, to get technically this f of g of x. If you kind of see what I'm trying to show you, we'd have to divide with this part to get like the triangle rule. So we would have f on top, f prime on bottom, and g prime here. Since we have f prime on the left, we would need the antiderivative divided by the g prime, like this. This kind of hopefully shows you how this rule where this rule comes from. So next rule is the u-substitution, or u-sub for short. It's basically the inverse of the chain rule. So before this example, we just had a linear insert. With the u-substitution, we don't have to have a linear function inside of it. However, here is the direct replacement or the undoing of the chain rule. So where we have g of x inserted into another function and then multiplied to the derivative of the insert. So this could be one. If you can see how this one is an example of what I have written on top, congratulations, you have very good understanding of math. And if you don't, that is okay, because that is why I make these videos, so you can eventually. So first I'll move the derivative part outside and write it as a product. And we see that the derivative part and the dx are already in place. And what about the first part? It has to equal to the g of x insert into an f of x. And we see that f of x is in the denominator. But this is also a function in itself, where there's just a negative exponent over the variable, so it gets put into the denominator. So technically, this can be written as 1 over x being the normal function, and f of x just being the g of x in this example. My bad for the poor markings, but it's kind of like this. This is just one of the examples. Another example would be sine of x times cosine of x dx, since we know that cosine of x is the derivative of sine of x, and they would take this place. This is incorrect, is it? Oh no, it is correct, because we would, technically we can write sine of x as 1 times x, and then instead of that x we would insert sine of x, so even if it's like a linear function. So anytime you have a function and its derivative present, you can use u-substitution. So how do we recognize it? How do we solve it? Well, using what I'm just gonna show you. So First, did we determine what the insert function is? So we have two functions usually present, at least. We have to find the relation between the two, which is the one of antiderivative and its derivative. So the capital F of x and the small f of x. And then the capital F, so this one, the underived one, undifferentiated one, is marked as u. Very often it's just going to be an insert function, so like e to the power of 2x, and the 2x becomes u. It's going to be no problem determining it. But with the example like sine of x, cosine of x, it gets a bit trickier. So basically, the insert function gets labeled as u, and then we take the derivative of it, so du over dx, to get the derivative, so g prime. I also color-coded each part that's gonna be relevant here, since it's the same differential of the same variable. Now, we would find what the f function colored yellow is, but let's save this for now as we have two approaches to inserting these u's into the formula. First one is the physics approach, where we replace the purple g prime with du over dx and then just cancel out the differential of x parts, like here, which mathematicians will hate, but we get our result all the same way. The second approach is how the mathematicians would do it, so we take this circled part as its own unit and try to replace it as a whole with something else. So we use this formula, use the triangle trick from last time, multiplying both sides with dx or integrating with it. However they do it, well, whichever way you choose to do it, it shows that I had a lot of experience and influence from physicists on chemistry course, that I preferred this method because I like cancelling out stuff. But doing that, we easily see we can just replace that entire part with du to get the right side we have on top. So all that together, it doesn't matter which approach you use, both are relatively correct. An easy example, you see how we can use it. So our example is e to the power of sine of x times cosine of x dx. So let me get our table up here. Maybe the derivative table would be more useful, but I'm sure you know it by now, or we can use this one in reverse. So we have the insert function, which is sine of x. We will label that as u. If we take its derivative, du over dx is cosine of x. However, I moved dx to the right, so we get the du already. So I'm just going to be using the mathematician's approach. So I will rewrite this with the insert, so I replace the blue part with u, I replace the orange part with du, and we get this function. Now I take the table from before, I get this, and I solve it, and I just get e to the power of u plus c. So literally just copy-pasted everything, replacing the x with u, that's it. And after we did, we have to insert the u back in to solve for the actual result, which is e to the power of sine of x plus c, and this is the result of this very easy integral. Like, if you see this, you don't think this is easy without any experience, without any rules. However, just using the rules that I present in my video, this should be all but easy. No, wait. This shouldn't be anything else but easy. Yes, that's the one. And yes, as long as you know basic derivative, integral tables, and some rules, you're fine. So let's get one more example, this time with the finite integrals to practice calculation. So we have x times e to the power of x squared. So here I marked it so it's easier to see that this is the exponent over x, so you wouldn't just carry the 2 in front. Technically you shouldn't be doing that unless you have the bracket over e to the power of x. But then again, that's a whole different story. So this is important, and then we have the x. And we are integrating between the x values of 0 and 1. So first things first, let's find our inserted function. That's easy. The inserted function is x squared. So we take its derivative and carry the ex to the right. We get the du equals 2x dx. However, now we need to find the part we're replacing it with, and that's x dx. And since this isn't just x dx and we need to isolate it, we divide both sides with 2. So we get x dx as it's here, and then something else that we're going to replace it with. So we're not going to be inserting just du most of the time, we're going to be inserting some other stuff multiplied or divided by it, like in this case, here. And now that we have that, so this constant is brought over with the derivative of this function, we can carry this constant out of the integral, so to avoid any distractions, and make it easier to follow the rules. And now we just simply solve the integration, but we need to be careful, where I marked it with a red line. Here we changed the x variable into u. We need to know that those limits at the start are set for x values. We are fortunate that the conversion into u limits doesn't change them for this example, as 0 and 1, when squared, stay the same. But if we had 2 and 3, for instance, at that step we would have to set them right or mark them correctly. So how to correct them? You put this bottom value as the x in this example, and then you get the u value of this bottom limit. Same for the upper, so 1 gets inserted in here, 1 squared is 1, so 1 is on top. Here it stays the same, which is fortunate for us. You can also just mark it like this, and keep writing it over and over until you replace it with x back. But it's important to understand this because forgetting this may cause you to get the wrong answer in many cases, especially if you're working with like angles and trigonometric substitutions, where suddenly instead of numbers, you're working with angles, radians. From degrees to radians, that kind of changes sometimes, so it is very important to follow that rule. So keep this marking or convert them into the u state, whatever you want. So, but again, since they didn't change, I can leave it as 0 and 1, and we just integrate this formula and insert the values into the function. So I integrate following this rule. I get e to the power of u. So we have this antiderivative. We insert this into the first one, then subtract this one inserted, and we get the result. So basically, e to the power of 1 minus e to the power of 0 is inside the brackets, times 1/2 of overall. E to the power of 1 is e to the power of 0 is 1, so our result is e minus 1/2. Since it's definite, we don't need a plus c. So again, when you use a u-substitution on a definite integral, you must update those limits too. Plug each x value of the limit into your expression for u. Here the limit happens to stay the same, but that is a pure coincidence. Always recalculate them, and once you change the limits, integrate and evaluate directly. And there's no need to substitute back, but you can substitute back if you don't want to solve for changed limits. Sometimes it's gonna be easier to change the limits, sometimes it's gonna be easier to just write these are x limits, because if it's a more complex equation like u is sine of 3x divided by cosine, in that case I recommend just leaving the x limits and just inserting that back. But then again, you're gonna do that math either way. Now, what about if we have product of two functions? Well, we will be using, it's basically the reverse product rule, and we have the following formula for it. It's sort of like u-substitution, but since there's two functions, we get u and v. So uv substitution if you want, but by parts is more commonly called. But how do we choose which will be which, and how will we fit them? Let's see. For the u, we have something called the L-I-A-T-E rule, liate. Don't ask me why they look so weird spaced out here, I don't know, but this basically means L for logarithms, I for inverse trig or arc functions, A for algebraic like plane powers and polynomials, T is for trig or trigonometry, and E is exponential. So in this order are the functions which should replace with u. So you go down the list. Do we have any logarithms in our integral? No. Do we have any inverse trig? And so on and so on. If we do have any as we're going down the line, then we label that function as u, which is the one we're differentiating. As you can see here, u becomes du and dv becomes v. So kind of like that. So dv becomes the one that's being integrated. Why is the order so specific? Well, as said, we're taking the derivative of u and integrating the rest. So it's probably that these functions are easiest to differentiate or harder to integrate at the start, and get harder to differentiate and easier to integrate the further down we go. As we can see, this doesn't really solve the integral, but it changes it and certainly makes it easier to solve in most cases. But there's two cases where there's one way to solve by parts easier and faster that I mentioned later, and there's one where we kind of loop ourselves and get the same function here as the result, but I'll also show it. So let's see an example of how this works. I'll do two examples, one very easy and one slightly harder. So our first problem is the integral of x times e to the power of x dx. And let's go down the Liate rule. Is there a logarithm? No. Is there inverse trig? No. Is there algebraic? Yes, x is algebraic. If we wanted to continue, we would see that the power of x is exponential. So a is before e, meaning that our x will be u, and everything else in the function, because this is our integral, and we have to set it fit. So whichever is the first function gets assigned u, everything else has to be assigned the dv. Now we need to differentiate the u and integrate the v, so we have all four parts to have our formula. So the derivative of u is written as du over dx, and the result of that is 1, since the derivative of x is 1. I just carry the dx to the around, so we get du equals dx. As for the integration of our dv, we use the table, and we get that v is e to the power of x. Why isn't there a plus c? Good question, let's check it out. So we have this, and we rewrite it as integral on both sides. We're integrating each side, so we're getting v plus c on left and e to the power of x plus c on the right. And technically it is the same constant, so it cancels out, leaving us with v equals e to the power of x. Now that we have our four parts, u, du, dv, v, let's set them into our formula. And yes, I color-coded it so it's easier to see where what goes, as I don't have a digital arm that I could wave around, and I'm not getting paid enough to do a face reveal to write it on the whiteboard. So now we see that on the right, the new expression we need to solve, we have, so basically this is the integral we have, this is the sort of solution to it, or a simplification to it, if you will. So this simplification will take the form of x times e to the power of x minus integral of e to the power of x times dx. So basically I just insert what's each color into it. And now we just basically solve this integral following the rule we have. And we get x times e to the power of x minus e to the power of x minus c. And I'm gonna factor out e to the power of x to get x minus 1, like in the brackets. And since the constant can be any value, it doesn't matter if it's plus or minus in the expression, as it will just be corrected by the different sign if we were to solve for it. So in the right result, minus c instead of plus c would also be the right result. It would just mean that the second c would have the opposite sign. That's just it. I hope this was a clear example on how to use it. If not, there is another one we're just gonna solve, and it's example number 2, just a lonely logarithm. You may be thinking, but wait, we have it in our table, that's easy. Oh yeah, let's prove it. We will be trying to get our table value using integration by parts, just to see how it works, plus to see that you can actually use it on seemingly just one function. So, let's see, natural logarithm is L, so first place in Liate, so it will be u. Now its derivative, if we still remember it, is 1 divided by x dx, because like dx is moved to the right, since du over dx is 1 over x, dx moved to the right, la 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 la. So we have our u and du. As for v, v is everything else. If we marked this as u, everything else is dx. So our dv is dx, basically just copying this. And now we integrate that, so basically just cancel out the d's on both sides, and we get v equals x. Again, the plus c cancels out, so we're chilling. Well, now that we have all 4 parts, let's insert them. And we get something interesting. We see that our first part is already the exact same as it is in the solution. So now we just need to solve this extremely easy integral. But let me give me a second. I'm gonna make it even easier for you. I'm gonna cancel out the x's because x divided by x is 1. So we're left with the integral of dx, or 1 dx, however you want it. And I don't think I need to add this stable part here, which perfectly solves this dilemma, but I will do it just in case. Integral of 1 dx is equal to 1x plus c. And since we have a minus in front of it, we have minus x plus c, because I'm gonna keep the constants plus. And yes, turn these two around so it starts with x and the natural logarithm is after it, but this is the same as this. This is our rule. This is how you get a lot of the results from the table, and I think you can do it for most of the ones on the table. If you want, you can. So, but yeah, that's basically how we get certain integral values. So there are many more tricks like cycle tricks, where the integral after integrating by parts gives us the same integral as the one we started with, the tabular method, partial fractions, Trig substitution, and probably some more. But for these, I will only show either an example or an image or a video that someone else did, as stuff other than maybe partial fractions is either slightly too advanced for our needs or can be solved and figured out with some of the out of the box thinking, which you will see in a bit. Tabular method is just an easier way to solve some, but I'll still show you just like the basic and where you can go to watch it. So, cycle trick is extremely handy when mostly using integration by parts that gives us the same integral we started off with. So I kind of hope this paints the picture, as the only examples I found were slightly complex and I don't want to scare you off. So the integral of a product of two functions, dx, gives us some uv, which we determined following the by parts rules, Lie or whatever. And then we get an integral of gx fx dx. And we see that we're going to call this original part of the function. So like the integral of the original function, we'll call it, let's say, capital I. And let's replace this part in the original, in this formula, this equation, with I. So we get I equals uv minus I. So we just carry the I to the left because they're the same. We get 2I equals uv. And then getting the formula to be set as the result of the original integral, because we want to solve this one, which is I, which is divided by 2. So the result of certain integrals that loop into themselves would be to divide this u times v with 2. This is just like example. You can look up cycle trick integrating on YouTube and everything. You're going to get plenty of results that better explain it on actual examples. I didn't have much time to find better examples than the difficult ones. But if you do, and if you want to learn this one, it's very good, but just thinking arithmetically can help you solve this. It's no problem whatsoever. Next up is the tabular method. It's basically integration by parts, but slightly easier or more visual. I'm not going into it, as the organic chemistry tutor explains it a lot better in his video integration by parts tabular method than I ever could. Plus his handwriting is a lot better than mine, as you saw a few slides ago. And if you want to solve it, well, I think his explanation will be a lot more helpful than my already oversaturated lecture, but basically determine what is like the changeable function, so which one is gonna approach 0 when differentiating, and which one is easier to integrate. And then you just integrate the one, so like this one is easier to integrate because it stays the same. This one is differentiable because it becomes 0 eventually. And then we just write this formula and we get the plus, minus, plus, minus. I don't really know these methods anymore. I remember partial fractions and the cycle method. But other than that, most of the integrals I work with are just simpler ones because, well, chemistry needs just the basic table and that's it. So these are just for those who are more curious about it. So yeah, this video explains it amazingly. Third up is the partial fractions, which is used for rational functions, and it works by breaking it down into a sum of two fractions. So it follows the example on the slide. So breaking down the product of the denominator, then we set two arbitrary constants like a and b, and then we expand both fractions to common denominator, so the original one, add them together and determine what the values of a and b are. Then the tutor explained this super good in his video, title shown on screen under the image. But long story short, break the product in the denominator, have each in its own fraction, set a and b as numerators in each of them. Then we expand the fractions back to its original denominator. So it's like a times the denominator in the second one plus b times the denominator in the first one. And then factor out the x, and you get two equations with two variables. Let's say this example here provided, to at least show you how to use it. Well, first, this simplification has already been done for us, but I guess the denominator was something like x squared minus 5x plus 6 or something, and the teacher was kind enough to write it as a product to make it easier. as image showed, we break it into multiple fractions, so each has their denominator as one of the terms or factors from the original denominator. So first bracket is in the first one, second in the second one, and then we set two arbitrary constants. Then we expand each of the fractions with to the common denominator, so we can add them together. This means that we're multiplying both sides of the left fraction with x minus 2 and both sides of the right fraction with x minus 3. So we get this. So let's just insert the a, so we get ax minus 2a and bx minus 3b. We put this all on the same division line, so it's easier to solve. Now, I'm gonna be only looking at the top part here because the bottom part is the same. We're treating this as an equation, so let's ignore this part in between. This is just a step product. So this is an equation. Left part equals right part. And since this is a fraction of, so like left part equals right part over some value, this value cancels out and it's easier to work with us if we just look at the top part like this. I'm imagining this left part as a linear function. So I assign some descriptive value of k times x minus n, where x is the variable present in both sides. So there's some constant multiplied to the x, some value multiplied to it, minus another value, as a linear function, of course. So I'm gonna try to rewrite this part here as this part as well. So I'm gonna factor out x out of all the terms that have x in it, and get x times a plus b minus 2a minus 3b, so this part edited, equals to 5x minus 13. Now let's color the terms with the same values, so with the variable and without the variable. I apologize, this one was colored orange instead of purple. Now it's correct. So this allows us to set two equations with two variables, because x technically is a variable, but not in this example, because it's gonna get cancelled out, because both of these have one x in them. So using that, we have the first equation, which is x times a plus b equals 5x. So we can kind of cancel the x's out and get a plus b equals 5. And then the second equation, which is minus 2a minus 3b equals minus 13. So first I'm gonna get a out, so subtract b on both sides. We get a equals 5 minus b. Then I'm gonna insert this in here, and minus 2 times 5 is minus 10. Minus 2 times minus b is plus 2b. We get this. Then we move all b's on one side and all the numbers on the other. We get something like this. Add them together, we get that 3 equals b. We insert the b back, get 5 minus 3 is 2. So our a value is 2, our b value is 3. We insert this into this part here, the introduction of arbitrary constants, because it doesn't matter what we mark them, it could be any symbol, we're just making placeholders to determine their values. So we insert them back in here, have that as the function we're integrating, so like this. Here is the integral sign that's missing, so we integrate this, and then we get an integral of the sum, so we use the rule. We have the sum of integrals, then we have the constant multiple. So I swapped the order, I apologize. So this one becomes this one, and this one becomes this one. So we carry the constants out, we get 1 over x minus 3, and we get plus 1 over x minus 2, something like this. And these are both integrals. This one is multiplied to 2, this one's multiplied to 3. That's horrible handwriting, I apologize. So there is a 2 times, now we use this rule we learned in the several slides ago. We get natural logarithm of the x value, and the x value is just the part. Can I change the color? I can, yes. So the x value in this example is just like the function that was here, so the linear, because we have a linear insert shortcut again. But in this example, the a in front of x is 1, so we're dividing both of these by 1. So, and since it doesn't change much, we don't really need to write these fractions like that. So yeah, this is a linear insert, so we insert it in there as if it was x. We have constant multiplied natural logarithm of absolute value of whatever was in here and whatever was in here. We copied it in, plus c because it's an indefinite integral. And after that, we get our result. 3 times natural logarithm of absolute value of x minus 2, so this part, plus 2 times natural logarithm of absolute value of x minus 3, plus c. And this is the final result of this integral. So basically that's how you use partial fractions. And on to our last trick, trig substitution. So if we remember the table of and the integrals of some functions, the arg ones, they have some weird formula with some bracket and even a root in the denominator, and they are the result. Well, yes, but no. Trig substitution is when we switch a certain factor for a trigonometric function like sine, tangent, secant, etc., and then we integrate by the angles instead of x. So something like this, we replace this formula with this one because, well, that's trig substitution, and then stuff cancels out, I guess. I think this is... Ah, yes. So I think this formula here is equal to a times sine theta or something. I don't know. Basically insert that and replace it. Then you have a new integral. You change the x variable into theta variable, and then stuff cancels out and you're integrating by the angle, and then you have to like convert it back with the triangle rule. If I'm completely honest, I don't even remember this anymore, so I'm not really in the position to explain it, but I can say that it exists and it's sometimes useful. But maybe on a higher math level, as for whatever I needed integrals in chemistry so far and some physics, we haven't really used this, so it exists, it's here, it's listed, but we won't work with it. You can forget it if you want, but if you want to learn it, you're welcome to learn it. This is the name. Just Google that. You're done. You're fine. And but I'm not going into it because, to be honest, I forgot. And what's the point in me teaching you something that I don't understand myself? However, I'm teaching you stuff that we will be using, and we're not going to be using this. So we can forget this ever existed. But if you're curious, it exists. Now let's see how we can approach solving integrals, just like a short summary, because this was a hell of a long video. So if we have a basic form, so it follows the table, one function integration, we just use the table and we're done. If we have a linear function as the insert, we use the linear composition shortcut, where we just divide the integrated outer function, so the antiderivative of function we had, with the a, aka the factor multiplied to the x from the linear insert. When we have a composite function and a derivative of the insert, or even just a function and its own derivative, we can use the u-substitution, which is our favorite thing. And if we have a product of two different functions, like trig and algebraic or exponential, we use the by parts integration. I made a mistake spelling something in the script. But basically, we will follow the Liete rule to decide which function is labeled as u, and then the rest is v and, dv, and then so on and so on. And yes, that is all that we need for our needs. I'm sure there's a ton of other ways, and if we need them, we will cover them, or they will be presented to you. If you want me to cover some, I can make specific shorter video where I cover them and solve examples to showcase them. So please, again, comment down below anything, any questions, any requests. Take me as your teacher, and I'm not afraid to help. I'm not afraid to explain the stuff that I didn't explain properly. I'm not afraid, and I'm not gonna flame you or anything. I'm gonna be eternally grateful if you find stuff that I can improve on. So please comment down below, join my Discord if you have any questions, yada yada yada. Follow me on Twitter, tweet, whatever. So yeah, all of that. Sorry, I forgot. Here's the mini test. I am sorry that I rushed the last part with those 4 tricks, but I think this lecture was much longer than most of you would have liked it. But I think it's important that I at least mention the stuff and send you in the right direction if you want or need to know more, especially if that source is of much higher quality than mine could be. Because, I mean, we all know that my video quality is average at best. I don't explain coherently that well, but I try. So yeah, mini test, 3 simple problems, just following the rules we covered. Here I had to clarify. Use top-down solving. First solve the top exponent and then solve down towards e. Well, because yes, that's how it's supposed to work. If there was a bracket like around the ex, then we would have 3 times x. But anyway, this was it. Thank you so much for tuning into today's lecture. I hope everything was understood. If not, again, comment down below. And I'll see you all on our next quest. Bye!